Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of Fundamentals of GPU Architecture, we're going to be looking at some of the research directions on branch divergence. Now, in this episode, we're going to be focusing on the first section and the first set of papers that deal with this, specifically talking about warp compaction. So let's go ahead and get started. Right. So, one thing that we haven't really talked about is, some of the problems with the SMPTE stack and other things that we've talked about when we've talked about the SMPTE core architecture, right? So, ideally, what you have is that you've got all warps executing the exact same control flow path. But as we saw with the need for the SMPTE stack, this isn't always the case, right? And you get divergence, right? So given the autonomy of threads, so this is just saying the threads can go different directions, you get branch divergence. And then modern GPUs contain special hardware to handle branch divergence, which we talked about extensively in terms of the SMPTE stack, and then later, more recent stackless architectures in proposed designs to get rid of some of the problems with the SMPTE stack, namely something like SMPTE deadlock and supporting more fine-grained locking mechanisms. Right. So while the baseline SMPTE stack handles branch divergence correctly for a lot of applications, there's some problems here. And we'll go into these briefly, right? So one of them is lower SIMD efficiency, right? So again, as a reminder, SIMD stands for single instruction, multiple data. So when we get branch divergence, the baseline SMPTE stack serializes the execution of each branch target. So what does that mean? So if we've got, say 32 threads, inside of a warp, right? Potentially each thread could go down a different path of execution, right? Depending on what the control flow looks like. So potentially we could have only a single thread active at a time, right? And so this really lowers our SIMD efficiency, right? So in the very worst case scenario, we're only actually executing one thread from each warp, and all those 32 threads end up having their execution serialized, right? So that's bad. So the second thing is needless serialization, right? So the serialized execution of each branch target by the baseline SMPTE stack is not actually required for functional correctness. So the GPU programming model does not impose any implicit data dependency between scalar threads in the warp. They have, to communicate explicitly with shared memory and barriers. So the GPU can interleave the execution of all branch targets of a diverged warp to make use of idle cycles in the SIMD hardware, right? So they don't necessarily, this, serialization that we saw, from the SMPTE stack, it's not necessary. It's just kind of an artifact of, the way the stack was designed. Another thing is the inadequate MIMD abstraction, right? So, because we force diverged warps to reconverge at a compiler-defined reconvergence point, the baseline SMPTE stack implicitly imposes a warp-wide synchronization point at each reconvergence point. So, while this works for many existing GPU applications, this, implicit synchronization is not necessarily a good thing, right? So as I mentioned earlier, there's problems with the SMPTE stack in terms of things like fine-grained locks, which could cause warps to deadlock, right? If, which again is something that's been more or less solved with more recent stackless architectures. Another thing is area cost. So for the baseline SMPTE stack, for each warp is only 32 by 64 bits, or as low as 6 by 64 bits. The area scales with the number of in-flight warps in the GPU, right? In typical GPU applications where branch divergence is rare, the SMPTE stack occupies area that can otherwise be used to boost the application throughput in other ways, right? So this could be instead spent on other things like a larger cache, more ALU units. So, we also want to address things like, we don't want to make the SMPTE stack too big, or maybe what are alternatives that are more area efficient? So how can we use these transistors more intelligently? But, the thing is, of course, this isn't a problem that nobody's thought of before. So industry and academia have both proposed alternatives to address the above deficiencies, right? And they can be categorized into a number of different research directions. So one of them is warp compaction, which we'll cover today. Then we'll also have intra-warp divergent path management, adding MIMD capability, and complexity reduction. So let's go ahead and start talking about warp compaction and that line of research that's going on. So with GPUs implementing fine-grained multi-threading, to tolerate long memory access latency, right? So this just means that we've got so many threads to cover the fact that, some threads will be waiting on long latency memory operations, right? So let's hide that latency with more threads doing different work. Since these warps are typically running, the same compute kernel, what tends to happen is they're likely to follow the same execution path, and they'll also end up having, branch divergence, around the same time. So this is this idea that all these warps are actually, even though they're completely independent, they tend to progress at around the same rate, right? And so because of this, each target of a divergent branch is probably executed by a large number of threads, even if it's not. Even if you get divergence within a warp, there's a large likelihood that if you start looking across warps, right, there still is, an overall number, a high number of threads going that same path. But again, they're scattered among multiple static warps, with each warp handling the divergence individually, right? So they're all handling it with, say, the SIMD stack, right? And so, maybe half the threads will be active and then half will be, waiting to execute their control flow path next. But if, say, half the threads, that are on a particular SM, right, are, let's say that all the warps are diverged in an SM, half are going one direction, but it's half of every single warp, then, potentially you could rearrange these threads in such a way where you've got half the warps going one direction and half the warps going another direction. So that's kind of the key idea here, or the key thing that we're trying to notice here. So again, we're going to be summarizing a series of research that exploits this observation to improve the performance of GPU applications that suffer from this branch divergence. So not for very regular applications, more so for irregular applications. So this includes things that are in the hardware, right? So ways to compact threads from different static warps into new dynamic warps. To improve the overall SIMD efficiency of these diverged GPU applications, right? So we want to have as many active threads as possible, doing, progressing things forward at the same time and not just be inactive. Right, so here static warps refers to the warps that are formed by the GPU hardware when the scalar threads are spawned from the launch kernel, right? So this is kind of intuitively how we think about our applications, right? So, consecutive, threads, if we say have a linear, grid, right? So every 32 threads will represent its own warp, right? So that's kind of the intuitive way to think about it. And we're talking about dynamic warps. We're talking about splitting those up and rearranging them. So let's first talk about dynamic warp formation, right? From 2007 to 2009, right? So they're trying to exploit this observation by rearranging these scattered threads that execute the same instruction into new dynamic warps. So just because we have got divergence of warps, perhaps multiple warps have the same divergence. So let's, kind of repack these threads so that we don't have this divergence, right? So the key idea is that divergent branches, dynamic warp formation, can boost the overall SIMD efficiency of an application by compacting these scattered threads, right? And so some follow-up work in 2011 identifies two major performance pathologies for dynamic warp formation. So one of them being that a greedy scheduling policy can starve some threads, leading to SIMD efficiency reduction. And the second is that thread regrouping in dynamic warp formation increases non-coalesced memory accesses and shared memory bank conflict. So, when we're thinking about how threads are going to access memory, we're generally thinking of, how is, say, a set of 32 threads going to access memory? So as a programmer, we might make this so that, these threads will access memory in a coalesced fashion. So they'll be accessing, a constant stride. So, we're accessing a contiguous chunk of memory. But when we start adding things like dynamic warp formation, all of a sudden that intuition goes out the window because, on the fly, all of a sudden in hardware, these threads are getting reshuffled anyway. So we're going to lose those contiguous accesses. So that's really the second pathology that we're talking about here. Now, all hope isn't lost, so these can be partially addressed with an improved scheduling policy that effectively separates the compute kernel into two sets of regions, and those regions are divergent and non-divergent coherent regions, right? So divergent regions benefit significantly from dynamic warp formation, whereas the coherent regions are free of branch divergence, but are prone to dynamic warp formation pathologies, right? So if, we're going to, this is basically just saying that if we can identify the areas where, we're going to have a lot of divergence, then it's probably useful for us to, do dynamic warp formation. However, in other situations where it's unlikely we're going to have, significant branch divergence, a lot of times we'll probably be accessing memory in, some contiguous fashion where we don't actually want to start rearranging any of the threads. It's often better that we have, large coalesced memory accesses, and we follow what the programmer intended in terms of trying to avoid things like shared memory bank conflicts. Right, so another paper from 2011, right, so on thread block compaction. So TBC, or thread block compaction, builds upon this insight with the observation that rearrangement of threads into new dynamic warps continually does not yield additional benefit. So instead, the rearrangement or compaction only needs to happen right after a divergent branch, the start of a divergent region, and before its reconvergence point to start a coherent region, right? So we don't need to continuously be doing this, but selectively do it at very particular points. So we note that the existing per warp SMT stack, so this is the one that we've discussed in an earlier video, we've got this implicit synchronization of threads diverge to different execution paths at the reconvergence point of the divergent branch, right? So merging these diverged threads back into a static warp before executing the coherent region. So thread block compaction extends the SMT stack to encompass all warps executing in the same core, forcing them to synchronize and compact at divergent branches and reconvergence points to achieve robust dynamic warp formation performance benefits, right? So we're kind of broadening the scope of what the SMT stack is managing instead of being very local per warp. So, however, synchronizing all warps within a core at each divergent branch for compaction can greatly reduce the available thread level parallelism, right? So some threads may or some warps may reach that reconvergence point early, and all of a sudden, even if they've got, say, no dependencies and could potentially move forward, they're stuck there. So what does thread block compaction do? So it settles for a compromise between SIMD efficiency and available thread level parallelism or availability by restricting compaction to only occur within a thread block. So GPU applications usually execute multiple thread blocks concurrently on a single core, right? So when we're scheduling thread blocks, oftentimes a thread block, each individual thread block isn't as big as a single core, so we can usually fit, maybe 2 thread blocks per core, 4 thread blocks per core, depending on how many registers we're using or how much shared memory we're using or the number of threads we're using. So execute multiple thread blocks concurrently on a single core to overlap synchronization and memory latency, right? So, TBC is basically leveraging this software optimization to overlap the compaction overhead at divergent branches. When warps of one thread block synchronize for compaction at a divergent branch, because we have another thread block there, that other thread block can make forward progress at the same time. So it extends the per warp SMT stack to encompass warps in a thread block, right? So instead of per warp, again, it's extending, the scope of the SMT stack. All right, so moving on to something slightly different, right? So let's talk about large warp microarchitecture. So in LWM, or large warp microarchitecture, so this was a paper in 2011. This extends the SMT stack, similar to thread block compaction, to manage the reconvergence of a group of warps, right? But instead of restricting this compaction at branches and reconvergence points, instead, it requires warps within a group to execute in complete lockstep, so that it can compact the group at every instruction, right? So this reduces TLP even more so than thread block compaction, right? Because everything's in lockstep. But what it does allow is it performs compaction with predicated instructions as well as unconditional jumps. So what it'll do, it'll split warps running on the same core into multiple groups, and then restricts compaction to only occur within a group. So it also opts for a more complex scoreboard microarchitecture. So, starting to add a little bit overhead and complexity that tracks register dependency at thread granularity. So this allows some warps in the group to execute slightly ahead of others to compensate for lost TLP due to lockstep execution. So there's lockstep, but with some caveats, right? Allowing some warps to execute slightly ahead, right? To make sure that we still are making forward progress and we're regaining some of the, overhead of forcing lockstep execution. So, as far as other papers that have been in this area, a little bit later in 2012 and 2013, we've got compaction adequacy predictor, right? So this extends thread block compaction with an adequacy predictor. So this, basically we want to know, what's a smarter way to tell, if it's going to be effective to actually compact threads into a few warps at each branch, and only synchronizes the threads at branches where the compaction is predicted to yield a benefit, right? So instead of just always doing it, we want to selectively do it only when it's going to have a benefit. So what this does is it reclaims some of the TLP lost to non-beneficial stall and compaction with thread block compaction, right? So we don't want to be doing compaction if it's not actually going to help us at all. And apparently this is a simple history-based predictor similar to a single level branch predictor yields sufficient accuracy. So we don't need a crazy complicated predictor in order to actually do this, right? So it turns out it's fairly easy. So the next thing is interwarp compaction from 2013. So it proposes a low complexity compaction technique that benefits wide SIMD execution groups that executes multiple cycle on narrower hardware units. So the basic technique divides a single execution group into multiple subgroups that match the hardware width, right? So instead of having, say a wide group that we're all executing at the same time, we divide it up into smaller subgroups for the hardware, right? So SIMD execution group that suffers from divergence can run faster on the narrow hardware by skipping subgroups that are completely idle, right? So, if we say have, 16 threads, right? And so 4 threads are going to go one path, 8 threads are going to go another path, right? So we can split these up into more fine-grained groups. The ones that aren't doing anything, we can skip completely. And then the other ones that will do something, we're able to execute faster. So but this requires something, right? Because we're not guaranteed that we'll have contiguous threads that are going to be, necessarily going down the same path. So each thread, again, can still go any path it likes. It has its own, the programmer sees them as completely independent, schedulable things, even if the hardware is more tied in the SIMD fashion. So in order to create these completely idle subgroups, they've got to add another mechanism, so a swizzle mechanism, that compacts elements into fewer subgroups at divergence, right? So, if you've got some threads going one way, you want to, swizzle that warp around so that you've got a contiguous group of threads that aren't doing anything, for example. So in 2012, there's a paper on simultaneous warp interleaving. So this proposes a simultaneous branch and warp interleaving, which extends the GPU SIMT front end to support issuing 2 different instructions per cycle. So they compensate for this increased complexity by widening the warp to twice the original size, right? So SWI co-issues an instruction from a warp suffering from divergence with instructions from another diverge warp to fill the gaps left by branch divergence, right? So again, we're trying to fill these gaps left by branch divergence by looking at, a larger range of threads, right? So the next thing we should be, considering with all of this is what it says. Not only how does it affect, overall execution, but how does it affect things like the register file itself, right? So to avoid introducing extra communication traffic between SIMD cores, the hardware compaction proposals usually take place locally on the SIMD core. So generally, we don't have a lot of inter-SM communication. It's only been relatively recently that we've had even the ability to do something like inter-SM communication through things like cooperative groups that provide, say, global synchronization barriers for all thread blocks that are on a particular GPU. Right, so since the compacted threads all located on the same core sharing the same register file, it's possible to perform compaction without moving their architectural states with a more flexible register file design. And so, let's talk a little bit about the register file and how things like rearranging threads can actually lead us to some trouble, and why we need to start thinking about the register file as well. So we've talked about the register file a bit, and the way that they're typically set up is we've got these large single-ported SRAM banks to maximize area efficiency, and the registers for threads in the same warp are going to be stored consecutively in the same SRAM bank, so that they can all be accessed together and read out together, right? And this is going to be a single wide port, right? So this allows high bandwidth register file access, while amortizing register file access control hardware. But as you may have already guessed, there's a problem if we start rearranging threads, and that's that things like warp compaction creates dynamic warps that don't obey this contiguous arrangement of threads. All of a sudden we have threads from different warps. Those should actually go to different banks. So of course this was noticed in this 2007 work, and they proposed a more flexible register file design featuring SRAM banks with narrow ports. This design has more SRAM banks to maintain the same bandwidth, right? So we need to be able to access more banks in order to access registers from potentially different banks if we're rearranging where the threads are with dynamic warps. Right, so in 2010, there's another work dealing with dynamic microkernels. Right, so in this work, they were targeting SIMD efficiency of ray tracing on GPUs. We haven't talked much about ray tracing on GPUs, but we probably will in the GPU programming course. So with dynamic microkernels. So basically, they give the programmer a set of primitives to break iterations in a data-dependent loop into successive microkernel launches. So this isn't going to do anything for parallelism because of the dependencies between loop iterations. But instead, the launch mechanism improves the load balance between different threads in the same core because we can go ahead and compact the remaining active threads into a few warps. So if we only have a few active threads, we want to make sure that they're all kind of going together. That way we don't have all this work spread out. So it also differs from the rest of the hardware warp compaction techniques in that the compaction migrates the threads with their architectural states using a per core scratchpad memory as a staging area. Right, so 3.4.1 summarizes a series of research that implements warp compaction in software, which does not require the more flexible register file design. Instead, these proposals introduce extra memory traffic to relocate threads from one SIMD core to another. Right, so now that we've kind of gone over all of these, these multiple, hardware techniques, we're gonna get into, can we do warp compaction, more intelligently in say software? So instead of changing the architecture, right? So on existing GPUs, one thing you can do to improve SIMD efficiency is through software warp compaction, right? So this is the same kind of idea, but you're using software to group threads to work items together according to their control flow behavior. So a very early work in 2000, right? So this is really before the era of GPU. Conditional streams apply this concept to stream computing, right? So it splits a compute kernel for stream processors with potentially divergent control flow into multiple kernels. And at divergent branch, a kernel splits its data stream into multiple streams according to branch outcome of each data element. So each of these streams is then accessed by a separate kernel and merges back at the end of the control flow divergence. So getting more towards, more into the GPU era, you've got this work from 2009 that proposed a parallel prefix sum to implement SIMD stream compaction, right? So, basically what we want to do is we want to recognize streams of elements with assorted task into compact substreams of identical tasks. So the same idea as the hardware, right? We want to match things together that are all doing the same thing. So this implementation leverages the access flexibility of GPU on-chip scratchpad to achieve high efficiency, right? So we've got this, shared memory, the scratchpad memory. What if we can use it to solve other problems rather than just, fast access to data, right? So what if we can use it to, to handle things like warp compaction, right? So another 2009 work proposed a deferred shading technique for ray tracing that uses stream compaction to improve SIMD efficiency of pixel shading in a complex scene with many material classes. So each material class requires its unique computation, and a pixel shader combining the computation for each material class runs inefficiently on GPUs. Right, so stream compaction groups the rays hitting objects with similar material classes. Right, so now we're again grouping things together, which is better for GPU hardware. So GPU hardware likes to all kind of run the exact same code contiguously, right? That's what really GPUs excel at. So things like matrix multiplication that are very regular. So in 2010, right, so a proposed runtime system that remaps threads into different warps on the fly to improve SIMD efficiency, as well as memory access, spatial locality. The runtime system features a pipeline system with the CPU performing the on-the-fly remapping and the GPU performing computations on the remap data and threads. Another thing from another idea from 2015, proposed CCC, or collective context collection. So this is a more compiler side thing. So a compiler technique that transforms a given GPU kernel with potential branch divergence penalty to improve SIMD efficiency on existing GPUs. Right, so it focuses on compute kernels in which each thread performs an irregular amount of computation at each step, such as a breadth first search through a regular graph. So it's something like breadth first search. I think we've got a typo here. In this kind of application, each thread is going to be tied to a vertex, and each vertex will have an adjacency list. And so we'll look through the adjacency list. But in a regular graph, some threads will have a relatively short adjacency list. Other threads could have a very long adjacency list, right? So they'll be accessing different amounts of memory and doing different amounts of work. So instead of assigning one node or task in other applications per thread, it transforms the compute kernel so that each thread processes multiple nodes with the node to warp assignment determined ahead of the kernel launch. So this transforms the compute kernel so that each thread in a warp can offload the context of a task to a warp-specific stack stored in shared memory. A warp that experiences low SIMD efficiency at its current set of tasks can offload tasks to the stack and use these offloaded tasks to fill up threads that went idle as they process a later set of tasks, right? So basically, this is just kind of doing a workload balancing, right? So if I've got too much work, we'll put it over here, and then idle threads can then pick up that work. So another thing is impacts of thread assignment within a warp. So in the baseline GPU architecture studied through the book, threads with consecutive thread IDs are statically fused to form warps. However, little academic work has gone into the static assignment of threads in warps or lanes in a warp. So this default sequential mapping works well for most workloads since adjacent threads tend to access adjacent data, but this isn't necessarily the case. So it's the case for very regular applications, but once we start moving to more irregular applications with a lot more data dependencies, there's really no reason why this is going to be true. Especially in something like graph algorithm where we're accessing different each thread is accessing a different vertex. There's no guarantee that once we start accessing the adjacency list and another vertex, right? There's no guarantee that what we're going to be accessing will be anywhere near each other or even have the same amount of adjacent nodes. Okay, so one of these works from 2013, right? So on SIMD lane permutation, makes the observation that sequential mappings of thread IDs to consecutive threads in a warp is suboptimal for warp compaction techniques. So a key limitation being, a key limitation is that when threads are assigned to a new warp, they cannot be assigned to a different lane, right? Or else the register file state would have to be moved to a different lane in the vector register, right? So in this work, they observed that the structure of the program biases certain control flow paths to certain SIMD lanes, And then this biasing makes it difficult to achieve compaction, since threads that take the same path tend to be in the same lane, preventing these threads from being merged, right? So we can't overlap threads on the exact same lane, so that's why they can't be compacted. So they propose several different thread mapping permutations that remove these programmatic biases to improve the rate of compaction, right? So make compaction even possible. Right, so this work from 2013 and 2009 exploit the fact that the width of the SIMD data path does not always equal the warp width. So for example, the SIMD width of 16 but a warp size of 32, which means that we'd actually need 2 cycles to compute something. Right, so so this paper from 2013 observes that when divergence occurs, if a sequential SIMD worth of threads are masked off for an instruction, then the instruction can be issued in only 1 cycle, skipping the masked off lanes. So they call this technique cycle compression. However, if the masked off threads are not contiguous, the basic technique does not yield any performance. So what would you need to do? So similar to as we discussed earlier, you would need some kind of swizzle compression technique to rearrange the threads. So you've got 16 contiguous threads accessing the compute units of the same SIMD width of, say, 16 in this case. Right, and so the last thing kind of in this line of work that we'll discuss is warp scalarization. Right, so other work such as this work from 2014 argues that the SIMD programming model is inefficient when the threads with a warp operate on the same data. So a number of solutions proposed, including a scalar unit in the pipeline for work that the compiler or programmer can identify as scalar a priori. So that just means we can determine, this is going to happen ahead of time, right? And so AMD's GCN architecture includes a scalar pipeline for this purpose, right? So, section 3.5, discusses this in more detail. And actually in the most recent architecture, I believe in the Turing architecture, there actually is a scalar pipeline on NVIDIA GPUs now. Now, this entire paragraph is basically just saying, okay, you've got 32 threads. Okay, all of your 32 threads are doing, say, A plus B, but it's the exact same A plus the exact same B. Well, if they're all doing that, there's no reason why all 32 threads need to, store that data or compute that single value. It should just be computed by a scalar unit, right? So just a single thread, right? And that's this idea of a scalar pipeline, right? So, long-winded explanation later. That's kind of the current state of the art and the scope of research as it relates to this idea of warp compaction. So as you can see, a lot of this work was done in the very early days of GPU architecture. So you see papers from 2007, 2011, and even some of the later work being in 2015 or so, right? So this work is very mature now in the field of GPU architecture. So next time, in the next episode, we'll go ahead and start talking about the second big topic on SIMD core architecture and survey this research, which deals with intra-warp divergent path management. But that's going to go ahead and do it for today. As always, feel free to check out any of the code that I have at github.com/coffeebeforearch. So, we've got stuff on, say, GPU programming in CUDA. So feel free to check out the other YouTube series I have called CUDA Crash Course, where we go over things like, vector addition, using unified memory, matrix multiplication, using cache tiling, and talking about coalescing, using the CUDA libraries, optimizing kernels for some reduction, convolution, histogram, etc. And we'll have later topics on doing, actually writing our own, kernels for, instead of dense matrix multiplication, doing things like sparse matrix multiplication. But that's going to do it for today. As always, I'm Nick from Coffee Before Arch. Send me any questions if you would like to know more about anything. And as always, hope you have a nice day.